So I'm going to go over the 2020 AP Calculus AB pre-response question number 2. Let's take a look at it here. A child has collected 5-cent coins and is preparing them to deposit in the bank by counting them into bags. For time t minutes, t between 0 and 40, the rate of the total number of coins remaining to prepare in 5-cent coins per minute is modeled by a decreasing twice differentiable function n. Values of n of t at various times t are shown in the table above. Okay, we'll take a look at that. We see t given for 0, 10, 35, and 40. And n of t, this is in coins per minute, would be -8, -11, -13, and -15. This negative seems coin per minute. This is just remaining number of points. So this you can think of his stack as going down. The remaining coins needed to be going is going down. So his coins per minute, this is kind of like the rate at which he's getting the work done. And it seems like he's learning as he goes. He's getting faster at getting the work done towards the end. 40 minutes in, he's doing about twice as good as he was at the beginning. In part A, we're going to use a left Riemann sum with the 3 subintervals indicated by the table to approximate this interval. Show the calculations that lead to your answer. Okay, so let's zoom out a little bit. I made a little graph over on Desmos of those data, and we see there's the learning. You can see this. We're going to be told that this was a decreasing, let's look at that again, twice differentiable function n. Okay, that we're seeing here. Remember, n is the rate. So areas underneath this is going to give us, would be coins. You can figure that out by remembering the units. This was coins per minute here on this axis, and on this axis we had minutes. So coins per minute by minutes, we're going to see that's going to be coins. And that's what we're actually approximating with this Riemann sum. So that's going to be part A. We were told to use left endpoints. So of these intervals, the left endpoints being chosen, we just have to find these areas. And I did that down here. So this is kind of written out in long form. That approximation. We're choosing to sample at 0, 10, and 35, the left endpoints. And we have to multiply by those intervals widths. So here I included the units again just to remind us what we're ending up with. This is -420 coins overall. And you can think of that as how much the stack went down over the first 40 minutes. Okay, part B, let's take a look at that. Part B, they're asking, is your answer from part A an overestimate or an underestimate for this integral? And give a reason for your answer. Well, looking at the graph here, you can kind of visualize that decreasing function going to the right there. All these approximations for those respective areas are under approximations. So this is a little bit tricky, I guess. The language used here is, I don't know, maybe ambiguous. I don't know. It was hard to Google this. I tried. As n is everywhere negative and is decreasing, any left endpoint approximation is going to overestimate. And I put here in parentheses what I really mean by that. Be less negative than the actual value of the definite integral. So I explain there further. Here, overestimate is meant to be any estimate that comes in greater than what was to be estimated. So the actual value would have been something more than 420 coins. We're missing out on these portions here, perhaps. You know, we don't know the details, but this is coming in at something that's less negative than maybe the actual value would actually be, if that makes sense. So I chose overestimate, meaning this to mean any estimate that comes in greater than what was to be estimated. So even if that is by being less negative. So part C, part of it got chopped off here in the clip, but it says using correct units, approximate n prime of 10 using the average rate of change of n over the interval 0 to 35. Okay, so average rate of change, it's not the tangent line, that's going to be a secant line. And if I go back to the graph up here, it's going to be this line from 0 to 35 that connects these. We just have to find the slope of that segment. And what it's approximating is the tangent line. Excuse me. What it's approximating is the tangent line slope here at 10. So I did that calculation down here. Just doing the slope between 2 points. Zoom back out. There it is. N prime of 10 would approximately be the change in the n value over the change in the time. So this is going to be, I guess it came out to be -1/7. Here the units on top were coins per minute, and on bottom they were minutes. So our units come out here, coins per minute squared. Okay, that was it for part C. D was getting into more of the interpretation of this, I believe, so I'll double check. Yeah, explain the meaning of n prime of 10 in the context of the problem. So remember, n was by itself, before it was derived, like taking the derivative of it, we were talking about a rate already. And taking the derivative of that, we're talking about the rate of the rate, you could say. So interpreting n prime at 10, we'd say at t equals 10, n of t, which is the rate at which the total coins remaining was decreasing already by itself, that was itself decreasing at a rate of 1/7 coins per minute per minute. I like to think of this as how he's getting better, the rate at which he's getting better at this time 10. You could think of it as sort of like him learning, the rate at which he got better at processing the coins, if that makes sense. So in E, they say it's known that n prime at 35 is -1/5, so, or 0.2. Is that it's t equals 35. We have the value at 35 is -13. So it's point slope, right? Yeah, this is the initial value. This is the slope. This is our change in time. F. What's F? Find the value of this definite integral here, where they've made a little change of variables here. Show the calculations that lead to your answer. This is U substitution, I believe we call it. We don't like this t over 4, so we just change it into u. Du would then be 1/4 dt, taking the derivative of both sides. Or you could simplify that, dt is 4 du. Making those switches, right? Remembering to change the limits because we've now changed to u as our dummy variable. T equals 0 gave us u equals 0. T equals 40 gives us u equals 10. You work this out. We get 4 times this integral here, and this is very convenient. We're taking the integral of a derivative, so we know how to do that. We just undo the derivative. That's our antiderivative. And we plug in the limits, 10 and 0. Everything comes from the table at this point, and we get -12. So G. We're talking about a second child now, also preparing 5-cent coins for deposit. For these same 0 to 40 minutes, the total number of 5-cent coins prepared by the second child for deposit can be modeled by the increasing differentiable function f, where f is a function of time. So assume the weight of each coin is 5 grams. We want to write an expression for the rate of change in grams per minute of the total weight of the 5-cent coins remaining for the second child at time equals 23 minutes. So, similar situation as to the first child. We're only now looking at the weight of the coins. I think my explanation down here will be helpful. So I'll go along with it. We can see all of it right there. at all times for the second child, we can say that f plus r equals t, where I've let r be the number of coins remaining to prepare, and then t, the total number of coins processed or not. This makes sense, right? There's no coins disappearing. The amount of coins that are finished, that's the function they gave us, finished processing, plus the number remaining to be processed would be the total number of coins. This is just coins here, though. We want to multiply this by the weight. So these numbers of coins by the weight per coin will give us a relationship between the weights. I just multiply by 5, and now this would be the weight of the finished coins plus the weight of the remaining coins would give us the weight of the coins in total. We're interested in the second term here, this 5r. This is the weight of the coins remaining. We can label that W here for weight. Rearranging this for this term, we get W is 5t minus 5f, and W prime at 23 would be 5, F prime at 23. Here we have 5 is constant, so that was the total number of coins. Doesn't change. In H, they're looking at a slope field and wanting us to explain why the following could not be a slope field for the differential equation dy over dt is equal to f prime of t for the function defined in part G. So remember, f was a function giving us the number that are finished, and so the number of finished coins, the ones we finished preparing, would increase. That's going to be an increasing function, and so have positive derivative. And I think I wrote that down here, to that effect. We were given that f is an increasing differentiable function, and so its derivative will be greater than 0 everywhere. Taking a look at that slope field, it could not work. We see it seems to be slope negative everywhere, the part that I can see here anyway. We just need one spot where it's negative, because this one's supposed to be always increasing, so its derivative would always be greater than 0. And we're seeing a bunch of negative slopes here, so this wouldn't work.